All right, so this is a video walkthrough of honors physics, third quarter, 2020, January or so, January 19th, 2020, assignment 10.1. It's a states of matter. That's the unit we're on, solid, liquid, gas, plasma, that kind of thing. And it's a Phet lab exploration. So let's open it up. And so it starts out with some questions for you. And it says, describe how atoms of a solid differ from atoms of a liquid. And the difference here is, I'm just going to kind of walk you through it. I'm not going to like go slowly and give hints because I have a lot to do. so atoms of a solid are locked into. They don't move around at all. Like you can draw a container like this. And you can say, well, that would easily be a solid because notice it's holding its own shape. It's not flowed out into a container, whereas atoms of a liquid, so the atoms of the solid, they are not vibrating. They're vibrating, but not enough to overcome the cohesive forces that are holding the molecules together. So they form a solid. You add a little more energy, they begin to vibrate a little more, and they start sliding around each other. Now they're still cohesive, they're still bonded to each other, but they're able to slide around each other, and that's a liquid. And so you can see that they're still all together. They're not up here, right? They're not up there. They're still all together because they've got the vibration of the atoms is not enough to completely break the cohesion of the atoms, but it's enough to make them sort of stick and move and stick and move. So they slide around. But if you have a gas, then the molecules have more energy and they're vibrating so fast they're bouncing off each other. And that's what happens then. Instead of just flowing like a fluid, they are a gas and they're everywhere. And so what happens? So in a gas, so in all three of these, the molecules are all jiggling with different energies. And I should use a different color. They're jiggling and moving around. In a solid, they're jiggling in place. In a liquid, I wish I had a finer tip thing, but this recording software doesn't. So in a liquid, some are going to have a little energy, some are going to have a lot of energy, right? And what happens for evaporation is whenever you happen to get a molecule, that high energy molecule, because the temperature is the average kinetic energy of all the molecules. Some of them are going to be highly energetic, some of them are not going to be highly energetic. So in evaporation, and this is just a side thing, in evaporation, when a high energy molecule hits the surface of the water, if it has enough energy, it breaks off and floats away. That's evaporation. Boiling is when you artificially add more energy. It could be a flame, it could be microwaves adding energy, but they all start vibrating enough that they bounce off each other so hard that they break the cohesion and form a gas. What happens to atoms when you heat them? They start vibrating more. That's what happens. Which is most likely oxygen gas? That's going to be this one, because this is a solid. This looks more like a liquid. And these are all over the place, right? Which is most likely liquid water. This looks more solid. What do you think? This or this? Now, what you need to remember about water is actually less dense as a liquid, as a solid, than it is as a liquid. So this is actually liquid here because it's less dense. And water is a polar molecule. They line up as they freeze. They actually create more space in between them when they freeze. So that's ice. And this one is steam. That's water vapor because it's moving all over the place, right? All right, so predictions. Do you think air can freeze? Well, yeah, anything can freeze. Can all substances change into solid, liquid, and gas form? It depends. That's kind of a weaselly word. I would say that's not a very precise word, because if you take it in its looser definition, the answer is definitely going to be no, because you can't make liquid wood and stuff like that. But can all elements exist in solid, liquid, and gas form? I think they can under the right conditions, not on Earth necessarily, unless we have a lab and we severely manipulate the conditions. Okay, so now we're going to open the lab. So you got to go to Phet, you got to go there, and you're going to look. So I went there already. Here, we'll go back there. So you're going to go here. That's Phet lab, and you're going to go to simulations and physics. And then you're going to scroll down. We're looking for this lab. It's called States of Matter. States of Matter. So back over here, scroll down, look for a lab called States of Matter. They're in alphabetical order. There is States of Matter. So we'll click on it. And then it'll bring up the page. And then it's got all this stuff. And we're going to click on it again right there to actually open up the lab. And then we're going to hit states, I think is what we're going to start with. Okay, so let's see what it asks us. How does solid neon or argon look compared to liquid argon or neon? Okay, so there's neon. There's neon as a solid. Argon as a solid. What looks different? The only thing I see, and I'm just going to kind of talk through this. I'm not going to write everything down on the paper. That'll be your job. Looks like the things that are different is that argon is a bigger molecule than argon's a bigger molecule than neon, right? But they're both jiggling, and notice they're jiggling all the time. Even when things are solid and frozen, the atoms are still jiggling. They're just not as energetic. That's the important thing. Because solid argon, that's frozen argon. Solid neon, that's frozen neon, right? So, how do they look compared to liquid? Okay, so there's liquid. Notice they're vibrating more. They're not flying around. Oh, there goes one. See, that's evaporation. It was so high energy that it actually escaped the cohesive bond that it had with the rest of the neon, but now it's going to float down again. Same thing with argon. So there's argon, bigger molecules, more energetic. They're kind of just generally cohesive, although occasionally they escape. But look at those things kind of sticking together up there too. That's really interesting, isn't it? All right, how does solid neon look compared to liquid? That's what we did. How about liquid versus gas? Okay, so what do we expect? Okay, back to neon. When there's liquid neon, right? What would we expect if we turn neon into a gas? Well, they're going to be vibrating a lot more, right? Because we've added energy to the molecules. And they're going to be vibrating. Right now, they're kind of sticking together. When they're solid, they're vibrating a little bit. But the vibration is nowhere near enough to knock them apart. When they're liquid, they're vibrating enough that they can't really stick together, but it's not so much that it blasts them apart either. So there's a balance kind of there between the cohesive bonds of the atoms and the knocking around from the vibration. So what we would expect is in a gas, they'd be vibrating even more violently, and as a gas, the cohesive bonds would not really come into play at that point. It would just be spreading out. And there's what we see. And just to go back to argon, because it asks about both. I don't know why it's doing both. It's going to do exactly the same thing. There you go. There's the gas. So energetic. They're just the energy of the vibration has way overcome whatever stick. You can see they kind of want to stick together. Some of them, if they hit at a funny angle or they hit really slowly, you can kind of see a little bit of a stickiness together, but not really much very at all. Okay, so that's that. How do oxygen and water molecules, just erase a bunch of stuff here, there we go. How do the oxygen and water molecules compare to neon and argon? Draw each. Why do you think that would be? Okay, so there's oxygen. What's different about that? Well, oxygen likes to pair up, and that has to do with the oxygen molecule and molecules want to, and this is chemistry now, which I'm only a minimal chemist, but molecules prefer to have completed outer valence shells. And so oxygen likes to bind up with other oxygen molecules. You usually find it in nature as O2. And water, there's H2O. Look at it, spins around a lot. Zoom, zoom. That's kind of cool. So water is actually polar. And if we don't watch it freeze in this lab, we're going to watch it freeze anyways. So how do they compare? Well, oxygen forms O2. There's two atoms of oxygen, while as argon and neon are both happy to be going around as single atoms. Oxygen likes to have two oxygens together, and water, of course, is a molecule with two hydrogens and one oxygen. So that's how they differ. What is the white part of each water molecule, and what are the red parts? The white part is going to be, well, the chemical symbol for water is H2O, right? So what that means is, so why am I, it's only making dots. That's so weird. Oh, I bet it's because it, interesting. Okay, so I'm trying to draw H2O and I can't. So too bad. Too bad for you. So it's got two H2O, two hydrogens, one oxygen, right? Oh, I bet I can draw here though. H2O. So that means there's two hydrogens and one oxygen. So oxygen is the big one, and hydrogens are the two little ones. And it's just interesting that water molecule sort of looks like Mickey Mouse. So have you heard that ice takes up more space than water? It does. Water is unique, practically, in that when it freezes, it expands. That's very unusual. It doesn't normally happen. So let's go take a look at it. So back here, we're on water. So we'll have liquid water. So there's the liquid water. Notice they're all bouncing around. They're kind of like puzzle pieces. They kind of fit in and out of each other and stuff, right? Now, water is polar. So as it slows down, what you're going to see is that actually the molecules kind of line up and there's not airspace in between them because it's too small for that. It's just space between them as it freezes. Now, gases do get frozen in there too, but that's not the point that we're making. The point that we're making, even if it's solid water with no other gas, when it freezes, those molecules kind of line up a little bit, and that actually makes the solid water less dense than the liquid water, which is very unusual, but here we go. So see, it's still jiggling, but they kind of lined up, and the polarity of water made it so that solid water takes up more space per molecule or per whatever unit volume, the unit mass, than liquid water. And so it's less dense and it floats, which is very important. So if I heat that up a little bit, add some more energy, that they start vibrating, and now it's liquid. And see, they can actually come more together because now their little interlocking parts can fit in together because they don't have to line up so much because they're moving, right? All right. So let's see what else. What else in this lab? What about other molecules? Do they take up more space? So let's do that. So here's liquid, and there's liquid oxygen. And if we have solid oxygen, does that take up more space or less? Well, it actually takes up less space, doesn't it? That's just nice. And I mean, this is more spread out as a liquid, of course, but the volume it takes up is actually less as a solid. Give me the same thing with, there's our liquid. That's quite a bit more space than our solid, right? For argon. So can you get the molecules to stop wiggling? Well, you'd have to take away all their energy. See this thermometer up there? It says 43K. So that's the Kelvin scale. So Kelvin and Celsius have the same amount of energy between each degree. The difference is that 0 degrees Kelvin is zero energy. And 0 degrees Celsius or centigrade, same thing, is the point at which water freezes at sea level. And so the point at which there's no energy is negative 273, I think it's 0.1 Celsius. So let's see if we can get we'll just cool these down more and more and more. Watch that. We're approaching negative 273. So the jiggling has almost stopped completely. Negative 272. Negative 273. There we go. So if I switch that to Kelvin, that's going to say 0. See right there? But the moment we do anything, there's 3 degrees Kelvin. Okay, so that's like, actually, space is about 2 degrees Kelvin. Outer space is not absolute 0. It's close to absolute 0, but there's a little energy out there. So yeah, so you can, I mean, in theory, you can get things to absolute 0. But no one's ever actually reached absolute 0. We've come within, like, I don't know what it is, thousandths of a degree. But absolute 0 is where all molecular motion stops. And so once to try to get there, everything inside would have to stop altogether. And, well, it's just impossible. But the interesting thing is, where is the coldest place in the universe? In all likelihood, the coldest place in the universe is in laboratories on the Earth, because we artificially lower the temperature so much. All right, so what happens to molecules when heat is added? They start jiggling more, right? And we're just going to keep jiggling. That's argon, you know. And so when you add heat, you add energy, you increase the jiggle, which the jiggle counteracts whatever molecular cohesion there is there, and it changes state. What is in the bubbles of boiling water? In the bubbles of boiling water is water vapor, right? Because you've added enough energy to the liquid water that the jiggling is strong enough to knock those water molecules completely away. So there is no cohesion there, right? All right, so there's another Phet simulation called Friction, and we're just supposed to go there and play around. And it's a book. It's not a very complicated, not a very complicated lab. So I'm going back into the Phet. There's Friction, and this is just rubbing 2 books together. So you can see they're solid books, right? But the atoms are jiggling. And there's a thermometer over there. And remember, heat is the total amount of energy in something. Temperature is the average kinetic energy of the molecules. So a cool glass of water can have the same amount of heat as a little shot glass full of hot water, even though they're different temperatures, because temperature is the average energy and heat is the total energy. So what's going to happen if I rub these together? Well, they're going to knock against each other, and I'm going to be using the kinetic energy when I rub it. That's going to add. I'm making them jiggle more, right? I just heated them up. So you can see the thermometer going up, and now that energy kind of bleeds off. Where is it bleeding off to? Well, those molecules are hitting air molecules and stuff like that, right? So that's what's happening. I'm adding, and that's exactly, if you take your hands and you start rubbing them together, exactly the same thing is happening. You start to feel the warmth on your skin. The warmth on your skin is the energy you're adding to make the molecules that make up the cells of your skin jiggle faster. So you are controlling the rate of jiggle of the molecules that make up the atoms in your skin. So that's that lab, and I'm going to sign off. And I think maybe I'll make another one real quick, or not. I got to see what's up with everything else. Bye bye.